Okay, so yes, this is a follow-up of the talk that I did last year about EAS and the fact that there was some use cases which were not correctly handled by the EAS. The goal was to fix some missed task placement, so to fix some task placement which were not correctly selected. And also the goal was to handle some new use case. So there is a patch set on the mailing list, which is based on what I did, what I discussed a year ago. And I think a year ago I was not speaking about the push mechanism. I was still mentioning the periodic. At LPC I mentioned the push callback.
No, we have some push stuff in there already, but not like your...
Do we... Oh,
somewhere in the loadout path, you can force migrate current.
Yeah, okay. When you are because you can't run, we schedule something then to push. Yes, I agree. But from a general point of view, similar, I mean, we don't have anything close to what we have in RT in deadline where we say, okay, this task, we should look to push that somewhere. So that's the point. It's not that far from what RT and deadline is doing. I even say it's even simpler because I want to minimize the number of tasks in this push list. Because I still want to keep that scalable. I mean, I don't want to end up 100 tasks, even if for mobile, I'm not sure that we'll have 100. But yeah, the goal is to have one task, maybe two, no more than that, to evaluate in this list. So yeah, one of the problems that we had was that the EAS is working only on the wakeup path. So when a task wake up, you select a CPU. But, I mean, even if it's probably the best placement at the beginning, few milliseconds or few dozen of milliseconds later, that might not be the best task placement anymore. And with U-clamp and the thermal pressure and so on, that's even less the case. I mean, once you push a task on a CPU, the thermal mitigation can just decrease the compute capacity and so on. So the goal was to be able to periodically move a task from one CPU to another one. Originally, the goal was to see how we can do that with the load balancing, but the load balancing is not scalable because you have to do that on one CPU and then you have to look at all the CPU and then in the CPU you have to select a task that you have to, I mean, that can't scale. Even if it can work on a mobile, that can't scale. So instead, the goal is to say, okay, when a task is dequeued, for example, let's see if we should push this task on another CPU. So I selected the dequeue event because that's easy to find. It's only one task which is dequeued at a time, so that's quite easy to put it in the list. So what we have on the mailing list right now, so we have this push mechanism for the fair. So usually we were only doing some pull mechanism except for with the stopper scheduling class and when we want to migrate the running task. But yeah, it was only one CPU wake up and try to pull a task. And the goal is now to add the push mechanism so we can have more opportunity. So we still want to find the more efficient CPU and we still want to find new event to look for the more efficient CPU. So typically, the one event is that when a task is put back in the enqueued list, we check if we can take the opportunity. So we are sure it's not a running task, So let's see if we can migrate that at that point. And when a task is alone, we are using the tick just because when you're alone, you are never put back in the enqueued and waiting list. So what have been implemented is really close to what is already available. I mean, it includes all the current use case, the mainline use case, except that instead of only looking at the spare capacity, it's looking at the cost of the OPP that will be selected in order to give another level of decision. But it's just another level. So we are still looking for the CPU with the lowest cost, and the one with the highest spare capacity will be one of them. but not, I mean, that just include more CPU, which can be selected. And then once we have a list of the lowest cost CPU, then we take another level of decision, which is, I mean, the least loaded CPU, but it's not the load in the term of the average load or the niceness. It's really about how much CPU cycle are used for now. I wanted to keep that simple, and the goal was really to spread the task on all the CPU. That's the main things. My assumption there is that we are in EAS, we are not overutilized. There is enough compute capacity for everybody. So it's just a matter of trying to be scheduled as fast as possible. That might not always be the true. There is a discussion with Pierre on that. But yeah, in the once we selected the CPU in the performance domain, we're still looking for the CPU with the lowest energy delta. For that doesn't change. I mean, the mainline kernel. So the difference is not that huge with the mainline. It just makes it easier to have another level of decision without normally impacting the power consumption compared to the mainline.
Why is it that you consider the CPU with the max spare capacity as not as the one which has the most idle? What's is it because we don't lock when we fetch the?
No, it's just that what really make a difference is the OPP that you will the OPP that will be selected. And the cost of this OPP. That really make a difference right now in the way we're computing the energy delta. But in fact, so the CPU with the highest spare capacity, for sure will be one of these lowest cost, because everything is based on the spare capacity. The opposite, not the spare capacity, but the capacity of the CPU minus the spare capacity. But you can have some other CPU that will end up selecting the same OPP. So that will use the same cost. Yeah. And that's this second level. As soon as you are selecting the same OPP right now, you will have the same cost that will be used. And because you're in the same performance domain, the utilization that will be multiplied by the cost will be the same. So they will both end up with the same energy delta. So that's why in this case, we can take another level of decision. You want to say something?
Just because the max spare capacity isn't just because it's the lowest cost, it's also the highest threshold until we spend more energy on all of the CPUs, right? Because we have to raise the OPP in case utilization grows on any of the CPUs. So there is an upside that isn't just cost to having this utilization balanced, and thereby, having max spare cap as.
Sorry, I'm not sure, but I mean, at the end, this will increase anyway for everything. The main things with the spare capacity is that you include the block task, the block utilization. So you can have some CPU with a large level of block utilization. So you will not select this one, mainly because you have some block utilization, but that doesn't mean that this one will appear sooner or later. I mean, not the point.
So the signal is wrong, like the spare cap signal could be wrong because of blocked.
So it will not. So the spare yes, it can not be the most efficient one because of the block utilization.
Okay.
I have a question.
Yeah.
As you mentioned, that one of the problems in basically placing only a task when you wake up is that you said, okay, you try to pick the best point, but 10 milliseconds later it's no more the best. But you have that problem also when the task goes to sleep. So anyway, if you compute power deltas or whatever you do, you always have that problem that then you would have shortly afterwards a new task waking up that changes completely the beam packing scenario. So
yeah, but
I'm not sure you don't really improve on that side, do you?
We improve. So the push mechanism improve in the sense that a task can then migrate on another CPU. I mean, it's everything. It's about you do a snapshot of the current situation. You see what is the most efficient. I agree that as soon as you take the decision, you might be wrong, but we can't do that all the time. So we need to do that periodically. Up to now, we're only doing that at wakeup. The goal is to add more event where we will just check if we are still on the best CPU and then migrate if needed. But I agree that as soon as you have migrated, maybe something else wake up and break everything. But I mean,
in this case, you evaluate migration when it goes to sleep, but when it wakes up,
not when it goes to sleep. When it's moving back from running to runnable, you run for a slice.
Okay.
You go back in the waiting.
Okay.
Yeah, it's not. It's not sleeping. It's just waiting for the next slice.
Okay, thank you.
And in this case, you might just move on another CPU.
Is it expensive, this selection of best power delta and everything?
Yes, compared to just doing that compared to SMP system, yes, because we are looking at all the performance domain, we are estimating, so yeah, it's not negligible. That's why we can't do that each and every time.
You could do it for multiple tasks that are runnable, right? So the cost will be divided by the number of, if you're doing the rebalancing for more than one task.
No, because we are, you need to migrate, you need to evaluate for if migrating a task will improve. But then once you have migrating this task, the snapshot have changed. So you need to restart to make sure that, otherwise that would say, okay, the solution could be, okay, all these 3 tasks must run always on the same CPU. In this case, I agree that you can just take all these 3 tasks as one. That could be a solution, but otherwise, no, you can't really make any assumption. So right now what the EAS is doing is that for each CPU in a performance domain, we check if the task will fit in the CPU based on the utilization. If it's not fitting, we just keep the CPU. What would be the cost or the OPP? And then if we have the same cost between 2 CPU, right, what I'm proposing in the patch is that which one is the least loaded or which one has the least number of running tasks. That's mainly that. And the point is that because we are not using, for example, the scaled slice, it's just that if you have 4 tasks on one CPU and 2 tasks on the other one, the maximum scheduling latency of one task will probably be 4 times 3 milliseconds for now, and on the other side it's only 2 times. So trying to balance, you get a chance to start running earlier without any power impact according to our energy model, which might not be true then, but yeah. And then between each performance domain, we are still looking at the energy impact, which means that we are not looking at the less loaded CPU between power domain. It's really in the same power domain, because in this case, you can have some power impact, even for the same utilization, because it's not no more the same OPP. And in the patch right now, we find for the energy efficient CPU, so at wakeup as usual, when a task, so I have added, I think Pierre suggested that I have added the misfit as well, which is quite simple, and it just, instead of waking up another CPU that will pull the task, we just migrate in directly. So I think that's quite efficient for that. Or when a task is stuck on a CPU, and by stuck, it's quite large, yes?
I have one clarification. So how do you decide whether a task fits on a task or not?
It's based on its utilization and the current utilization of the CPU compared to its compute capacity. And we have, and then we have all the util max or util min that can bias the decision. So what is a stuck task right now? So it's when you don't have wake up anymore because of your clock max, for example, or you can have a wake up but at a really low pace. And by really low pace, it's just that if you have a task, you can easily go above 20 milliseconds on the same CPU as a runnable state. and 20 milliseconds, even 40, that's quite easily. I mean, with a 3 millisecond scheduling, if you have 5 tasks on the same CPU, you can easily wait quite a long time. And in this case, it's worth evaluating. Or if you have if you have some thermal and system pressure, so we'll lower the CPU, the utilization will increase slowly. I think that's also a thing that Case is trying to fix. But yeah, you can stay stuck on the CPU for quite a long time, either before becoming misfit or overutilized, and then you have to share the CPU. So right now, by stock, the rules is quite simple. It's just that if you have your utilization, your UTLS, or your runnable, which become above the compute capacity or the uclamp max, because it means that you can be in a situation where you will never become idle anymore. That's pretty simple so far.
Yes, it sounds like the shared CPU time problem is at least because the load balancer is turned off when your EAS is. So that's kind of like, because of that, we have to now go do this because that's turned off.
Yeah, and because we want to pack the task to optimize the power consumption.
I guess I was thinking, like, why not just turn that back on, the load balance, and then
because the load balance then will just screw up everything at the point.
But kind of can we tweak that?
Oh, so this is kind of turning on the load balancing button in one specific place, right? It's like not exactly turning it back on, but adding something that in one place will kind of work like load balance.
No, because at the end we are still using the goal is to keep using fine energy efficient CPU. So we are still looking for something efficient.
Yeah, right. Yeah. I'm not talking about the goal, but at the time when you do things, right? Because it is like, in addition to wakeup, you want to do something in other place to kind of, replace a non-existing load balancing in this case. Like because if you don't do this, then you have the problem that it's so it might be more efficient to run somewhere else, but it's kind of got stuck here because. Yeah, so you need to unstuck it somehow.
Yeah, but the main problem with the load balancing right now is that it doesn't scale quite well because you will have to look at all the tasks to see if if you have this periodic load balance, the task, so when CPU wake up, start to look at all the other CPU, and inside all the other CPU, start to look at all the runnable tasks. In this case, the goal is to say, okay, we take one at a time.
That's idle load balancing, but there's also active load balancing, right?
In this case, it's, there is the idle and the active, yeah. But yeah, the goal there is that you can even if the CPU is already busy with one task, you can still push one task on this at the point.
So I don't have a problem with that.
Yeah.
Just two notes. First of all, the shared CPU time case.
Yeah.
If you do that for a very long time, of course, it will become overutilized unless your max is messing with that.
Yeah.
And the other one, you always risk, if you don't have any wake-ups, or you haven't had a wake-up in a very, very long time, then your utilization values are essentially wrong, outdated. Your
util average, you mean, but normally your UTLS should remain, and that's what we mean by long. That's really the point also.
What do you mean by long then?
I mean 20, 40 milliseconds, a dozen of milliseconds start to be long. That's the point. And you're not overutilized yet. After 40 milliseconds.
Yeah.
The goal is to not reach the overutilized that will just screw up the packing of the EAS. But still we have some tasks, and I will mention that a bit later on. If a latency sensitive task, we can say that, has been scheduled out, then it will have to wait for 10, 20, 40 milliseconds, maybe. Yeah. So all this is this current implementation are made really simple. Yes?
earlier you mentioned that you do the push only when task becomes runnable again from running and not when it goes to sleep.
Yeah.
So like why not that use case? I have an example where it would be very useful.
You mean when we go back to sleep?
Yeah, it's like if I know that certain task is going to sleep and the code is becoming idle, I have an instance where idle stealing tries a couple of times but fails every time. I see like the code is idle for multiple ticks and it's not able to steal anything. It's a single software machine.
Okay.
And I wanted to do exactly that push some task.
Oh, so yeah.
Where it is giving up, like forced load balance and like here a couple of times on forcing the load balance and the task.
Yeah, but then there are several things. Then with the EAS, it's not because a CPU become idle that pushing a new task is more efficient from a power point of view.
But if I'm not caring about EAS, right? Every code is going on.
So okay, so yeah, right now the push I enable the push mechanism only for EAS. We might want to consider to enable that for other cases in SMP instead of doing idle load balance. Maybe I don't know. But yeah, I never considered that so far. Because for the idle load balance, for now, there were no real strong requirement to do some push mechanism. But I don't know. Peter, do you know why we have never done the push mechanism for the fair scheduler?
No, it's just not one of those things that ever happened. So idle load balancing has been an issue, and only today I think some guy from Hyven posted the patch to rotate the idle load balancer.
Yeah.
Because it is very expensive on big machines. Many years ago, Venki and Suresh, then still at Intel, posted patches to make idle load balancer per node, and have some issues that I think are fixable, but then they left for Google and they never go back to those patches.
Okay. But yeah, I was a bit. I haven't replied, but or maybe we can discuss that for the idle load balance. How it's unfair because the CPU is idle. It's because it's trashing the cache. Normally, idle load balance run on an idle CPU, so you're not preventing anybody to run. And then, as soon as you have a task, we abort the idle load balance. So normally, we should not break the fairness of the task.
Yeah, so I'm not sure. We can ask that.
Yeah, I was planning to reply to him because, I mean, if you're idle, the only thing is that, yes, if you trash the cache or if you play with some memory access, maybe, but yeah.
It's a latency thing too, right?
Okay.
If something else needs that CPU while you're...
Yeah, but so we have a lot of abort. I mean, when we start the idle load balance, we have a lot of place where we can abort really quickly. So there will be a latency, but normally being on a NUMA node, that should not be that huge. I mean,
Yeah, I'm just trying to say,
or maybe we should add even more abort tests to say, okay, just. But yeah, that's yeah.
I'm just curious. So I'm just maybe I don't understand everything, I guess. But I mean, when you say push, I mean, is it basically let the idle just say I'm idle and someone else can push to it? Is that?
No, for me, I'm not. We were discussing about being idle, but in my case, I don't have any notion of idleness from the CPU. It's more on when the task is on a CPU, and it's let the CPU for another task. In this case, we say, okay, should we wait on this CPU or should we take advantage of before being put back on the runnable list to be pushed on another CPU, which can be idle or not?
So I mean, could this use some okay, so the push-pull logic, or actually push logic of the RT task has the CPU priority.
Yeah.
So I mean, if you had, I know it's just basically based off of priority, but it's pretty much lockless algorithm. If you had all the CPUs having some sort of priority level or something based off of how many tasks it's running, And I don't know if it was able to adjust like its priority somehow. I'm not exactly sure how this would map. But then when you are a task like, oh, I mean, like there's many tasks here. Kind of look to see, how other CPUs are. You could look at a single location and say, oh, that CPU is available, and push yourself over, like push some tasks there or something. Or?
Yeah, but in this case, I think we have the opposite scalability problem that I'm trying to fix with EAS. That when a task, if you have to look at the load of all the CPU around to see where you should be pushed, every time. In the non-EAS case, that can be problematic, I think.
Yeah, so idle load balancer is, I don't know. So currently when we wake up task and the non-EAS case, we'll do the search idle sibling and it will look in the L3. And if nobody's idle, then it will just dump the task there and forget about it. And the regular load balancer is a pool balancer. But we also keep CPUs idle. So if we don't do anything, this L3 will become overloaded and stay overloaded because all the other CPUs are idle. So an idle load balancer is a load balancer that runs on a random idle CPU and tries to alleviate this problem by pulling tasks. And then that CPU is no longer idle, and then you select another CPU to go pull tasks if somebody is overloaded. So it avoids that problem. We could also go and detect the I got overloaded situation and push at that moment, I suppose. And that might also work.
Maybe.
What is the harm in this? We use it to mask it.
But we have an idle CPU now, and that all on its own is a scalability issue.
Sorry. So yes, that is stuck. So yeah. So in addition to the patch on the mailing list, the first proposal will be to be able to preempt for short slice. Oh no, that's the other one. I have several ones back. Yeah, the preempted short slice. So we are able to set a slice per task with the ability that normally the short slice should run first. The main problem is that because of the frequency scaling or because of the asymmetry, if you set, I want to run 1 millisecond, it's 1 millisecond at the max frequency, and you might end up running 2 milliseconds, which means that after 1 millisecond, you will be preempted. And you will be back on the enqueued list, and you will have to wait for the other others to run their slice. That can be quite long. That's another thing I have an issue with the parity, run to parity. But in this case, that could be an opportunity to say, okay, let's see if there is another CPU where I can run earlier than just staying on this to try to reduce my deadline. That's one thing. The other one is that right now I was mentioning only if a task is stuck on the CPU, but we know that the profile of a task can change. So when you wake up the task, you wake up based on the past right now, but the new behavior might be different. So being able to detect that the task has changed. So I would say if it's shorter, that's fine, because you will go back to sleep. But if you start to run longer than the previous execution time, then that you might consider to migrate that task in advance instead of just waiting to be a misfit or overutilized.
Why would you? What's the advantage of not waiting until misfit hits?
Typically, for example, I was mentioning if you have 4 tasks on the CPU with the same skate slice, with the default 3 millisecond skate slice, for example, you will have to wait. You will have to wait for the other one to take their slice. If there is another CPU with only 2 tasks, you will have to wait half the time before being able to be scheduled.
Would you see that in the util average if it's like such a preemption equals schedule thing?
You mean this?
Oh, sorry, I thought that was one proposal.
No, that's true. The goal is to extend the case where we want to push, to evaluate if we need to push. And then, yeah, another thing there is that maybe just by default, if a task is on a CPU runnable more than 32 milliseconds, even if you don't have anything, maybe it's worth looking at another better CPU, I don't know. Just instead of trying to find an event, and I was mentioning half of the life period of the pelt because usually you can see something different. Yeah.
Isn't it related to what Kais did with the...
Sorry, what?
Isn't it related to what Kais did with the when you run for so much time on the little CPU, for instance?
This one?
Yes.
Not especially because, so yes and no. It's just that because we're able to push, let's see if there is another CPU. In this case, it's not really related to the fact that you're misfit. It's just that now that we can push a runnable task, maybe it was to do that regularly. Because we are doing that for only one task at a time. So we are bounded in the time to, I mean, the overhead is bounded. We will not start to look at for the 10 tasks on the runnable queue. Yeah, the second proposal is that right now I have this simple list-loaded CPU, which is mainly looking for the CPU with the lower number of runnable tasks, and if they are the same, looking at the runnable average. One thing that I would like to add is take into account the slice of the task. So I would say if you have the default slice, maybe you don't care. But if you set a custom slice, and if you have several CPU that will have the same cost, looking at one where you will be able to preempt directly, maybe that would be a good in for latency without any power impact. That's one thing. Maybe there are other things, I don't know, but at least this one seems to be a good way to improve the scheduling latency, or the scheduling delay.
Now you're back in fine energy efficient CPU here.
Yes.
Yeah, okay.
Yeah, that's really the second level. When you know that all the CPU in the performance domain will have the same power cost or energy cost, and you have to choose. Right now, I'm only looking at the one with the lowest number of running tasks. But maybe instead of doing that, we should, okay, I have a custom slice. Which one has on which CPU I can run directly instead of waiting? For example.
Otherwise, it's find best CPU, your new function.
Sorry?
It's called find best CPU.
Yeah, I think, or select best CPU, I don't know.
Okay,
yeah, select best CPU, yeah. Yes?
In this case, there is idle time. Isn't it going to increase migration, the number of migration, and also the stability of the...
Sorry?
If there is enough idle time and we just run the EAS at wakeup, if we are pushing task,
yeah.
Right now it's only done when we are supposed to be overutilized. But if we are doing this all the time, isn't it going to increase the number of migration and also the instability of...
that's something that I need to consider, yes. But I would say normally if we are migrating, if we decide to migrate, to increase the number of migration, that should be for a good reason, to improve the energy or the scheduling delay. So yeah, I mean, increasing the number of migration, it's not a problem as long as you get a benefit behind that.
Yeah, but the fact that we stay a long time in a little CPU,
yeah.
It's also it allows to have a good prediction of the OBPs that this CPU is going to select. So it's sometimes better to stay on the same CPU. It's more stable as well.
Yes, but
if let's say we have two tasks
yeah.
on a little CPU that wake up, we know that we are not going to raise the OBP at the end. If we see that the tasks have been running for 10 milliseconds, we are going to start migrating one of the two tasks to an idle CPU, let's say.
Yeah.
But in the end, if we had kept these two tasks in the little CPU, the OPP would have been raised. So it's a useless migration in this case.
So I would say that depends. If those two tasks have set a short scheduling latency, you will improve the execution time of those tasks by migrating one of the tasks on an idle CPU. If they haven't done anything, if they are just clumped, I agree that doesn't make any difference. But that's why it's a second level. I mean, the goal is to get a benefit. Either your scheduling delays is improved, or you will finally be able to lower the OPP of your little CPU. But I mean, the goal is not to migrate just for no reason. The goal is to improve one of the parameters. And the last one is just, right now it's everything, it's only about energy efficiency. So at the end, it's really what we are comparing delta energy. And maybe sometimes it's a bit too strict because the delta energy is not that huge. And we will benefit, typically if we're looking at the scheduling latency in the sched slice, and we can have some short running task that will be packed on the little cluster, for example. And mainly because at some point, otherwise migrating one task on the big core will have an energy impact. But should we accept this energy impact in favor of a better responsiveness? That's something we might need to consider. And that would mean some change in the task fit CPU and the energy delta comparison. And that would include more change in the find energy efficient CPU. And the main worry is that how to be able to bias the energy decision, which is right now really binary, you are above or below. Then, okay, you are above, but how much you are above, and does it make sense? We need to find that, and for that I don't have any solution. But maybe at some point we need to consider that the energy, even if it's the strong argument for us, the energy model is not perfect. So when you have, 100 microwatt or microjoule of energy difference between two CPU, does it make any real sense in reality to say, no, not this one because of this 100 of microjoule of difference?
We are talking about these fake energy models, and it doesn't make sense.
Yeah.
Another thing is how do you test those things? When you have our customers, right, with their applications, those fine-grained things they will probably never find out. So we don't have anything. I mean, somebody could say we go this way, the other guys say we go this way.
Yeah, you mean for this kind of? Yeah, that's right. I don't have the solution right
exactly.
now. I think it works, but I don't want to add another, not to say, okay, I accept a margin or whatever. Because I agree that everybody will come with their margin value.
It's just, we don't have those simple benchmarks where you can say, okay, my number is higher, so it must be better. We don't have this.
I agree on that. And then, so when I was testing all this and the previous talk as well, there were two main open issues. So the first one is that the overutilize is far too aggressive. And I was trying to, when I was running speedometer with Android, I mean, when you look at the CPU, I think, it's all the CPU in average are idles 60% of the time, but we are overutilized between 65 or 80% of the time of the test. So there is a mismatch.
Can you not just change the signals, from some util-S to some util-average?
Yeah, that's so. That's one thing. I did two things there that has improved for my test. That's not using the sum of util-S for the task fit CPU and overutilize, and also increase the level of the overutilized detection to the compute max capacity, 1024, because we can easily go above the compute capacity. That's one thing. Another thing is the run to parity. It's so when you set 1 millisecond slice for, so I did the test. I set 80 milliseconds for one task and one millisecond for another task. So the 1 millisecond task wake up, preempt the other one. But if it exhausts this 1 millisecond, then it will have to wait 80 milliseconds before running. And I was expecting that he has to wait 1 millisecond and then schedule back. In fact, I was expecting that the minimum slice was the granularity between switching between tasks. Because there, I mean, the impact is quite huge.
Yeah, now like you say, yes it does. I'm not quite sure what the easiest way to picture is, but it's a good point.
Yeah, I was surprised. But I never really tried to increase the slice. Yeah.
It's one of those hacks that actually make a difference.
Yeah, but if I disable run to parity, I think that we go to the opposite. That for each and every tick we might switch, and so that's why I was thinking that using the min slice on the run queue can be a good pace between switching between tasks. Because if you have a task with a short slice, normally it should run not that huge, but you want to make sure that it will make progress quickly. So that was one thing that I have discovered as well. That in this case, yeah. Yeah. And I think that's it. Yeah. Do you have any question? How do you feel with adding the sketch slice in the energy-aware scheduler in order to make a decision? Do you think that? I think that could be a way to improve things, but I also think that we might have to be as the energy, which is the most difficult part. But I would like to go step by step. I
don't know how to test it.
Yeah.
If you have test cases where you can.
But for that,
very little people, very few people change this.
Yeah.
Right, from those default 3 milliseconds. I mean,
yeah, that's another thing as well. How to test that on how to hack AOSP to easily hack AOSP.
Probably they haven't started to play with it because the amount of work you have to do to test out those things in your environment. Yeah. If you have a couple of them, it's pretty overwhelming, or it could be. And then, but another question for your new fine energy efficient CPU, the behavior of UClamp max constraint task. Did it change in the layout of fine energy efficient CPU? Do you add some functionality there to treat those tasks differently, or is it just the push-pull mechanism then when there is a UClamp max task?
So I'm not sure to get...
With cases patched like 2 years ago, so we let UClamp max task into energy efficient CPU.
Yeah.
And they can mess up the energy calculation, for instance.
Yeah.
Now I know you have the second level of if the energy model doesn't give you anything, then you test on number of CPUs or runnable.
Yeah. So this fixes a number of with UClamp max. This fixes a number of UClamp max misbehavior.
Okay.
Yes.
It wasn't clear to me. Okay.
Yeah, that's a way to But then there is this discussion with the load average versus runnable average of a task that is UClamp max to a value. Mm-hmm. But yeah, that's one reason to that's
the one you have on the current patch set.
Yes.
Okay, cool.
Yeah.
So where's the whole UClamp max versus UClamp something at the moment? I don't understand what's this talk, but the guy can't show up.
It's. I think it's stalled. I haven't seen anything. So he sent his new version just before, but the last one was before SPM, the previous. Can't remember. It was 6 months. Right now, my main worries with this solution is more the implementation, and there is some. For me, there is things which are a bit hacky, but and we still have some kind with the UClamp min. For me, you are underutilizing the CPU.
But one of the concerns he fixed in V2, there's an additional patch at the end.
I have seen, but that's for me that's look a bit hacky, where you're tracking one task that have finally not a uclamp max, and then you use that to. I haven't looked in detail, but it's tracking the one runnable task that doesn't have uclamp and might lose its fairness. So you bias finally the utilization, you bias the uclamp, the sum aggregation to compensate that. That doesn't really, for me, look good.
But I think this patch was made because you brought the argument that the sum aggregation breaks the fairness.
Yes.
But so to come back to the discussion right now, if we right now when we have uclamp max task running on one per domain, we are balancing the task on the number of we are balancing the CPUs with the number of tasks, but if these tasks don't have the same fairness, then we are also breaking the fairness.
Yeah, except that my point is there is a huge difference between there is one task that doesn't set any uclamp max or uclamp min value, and this one will see its fairness broken because of other tasks. That's the problem with the sum aggregation. What you're mentioning is that if you have tasks that set a uclamp max of 1, for example, with different niceness, the sharing, the running time sharing will not be aligned to the fairness, yes, but I mean, on the same time you say that you want to run at the lowest possible performance level. Yes. So you will have all the performance that you wanted at the end.
Yes, but so uclamp max is completely fine as you want to give a hint about the OPP you want to run at.
Yeah.
So if you say that you have a uclamp max of 1, you say that the task would like to run at most at an OPP matching utilization of 1. But it doesn't say anything about the CPU share that this task would like to.
No, but the share of the CPU is that when you are using all the compute capacity of a CPU, and then you have to share this compute capacity, you use the niceness to make sure that the share will be fair. Now, if you say my task wants uclamp max 1, that mainly means that the integral of this for 1 second will be 1 multiplied by 1 second. So you don't need more than 1 compute capacity per second, typically.
It just means that the OPP must match.
But the end result is that, I mean, you don't need all the compute capacity.
And so it means that you are setting uclamp max, the uclamp max setting as a bandwidth hint, which is so it's going to.
No, but you set a performance in to say my task doesn't need to run at most at this value. Yeah, but that also gives you a maximum compute capacity that you can get.
No, because if you set a uclamp max of 1 on the CPU, it will run at the lowest OPP, which is not 1. So you will get more.
Yeah, but why did you set 1 if you need more at the end? If you set 1, you mean that you don't expect more than 1. Then from a reality point of view, there is no OPP to say capacity 1. So that you will use the lowest compute capacity. So you will have much more performance than was expected. So you can't complain that you don't have you see the point, you can't complain that you have all this if you say that I want the lowest possible value.
Shall we take something also does seem weird. Because then you can actually end up above the max of any of the tasks.
Sorry, which?
If you have 3 tasks, all with a max of 750, say something weird, and you sum them, you'll be at 21.
No, So So I don't think that the sum is the right solution. Sum of a uclamp max or min. I think there are some problems. With uclamp min, it's obvious that you have the tasks that want to run at highest frequency. You set 1024, And it's mainly say that you will not be able to use that CPU for any other task because you will be overutilized. But even that, beside that, the current implementation, is biasing the pelt and biasing this load to compensate the fact that it can be unfair of tasks that doesn't set anything. If you haven't set anything related to uCount max, you should not be impacted by uCount max. Once you start to set uCount max or uCount min, you will have an impact on the performance, which means that you will have an impact of the compute capacity available for you. So the niceness become after that.
Yeah, so uCount max is no more a hint, it's something which comes before niceness.
No, it's not becoming before. It's just that by that you say that more than the niceness, you just say uCount max 1 is just say that you need a compute capacity of 1 per second, for example, for each time window, whatever is the time window. That's it. You say I don't need more performance to do what I want. So why will you complain if you have
more?
Yeah.
You only set this at 1 if you have a very short runtime. And now you're complaining I run longer. That doesn't make sense.
So it was an example, but if you're running a CPU with a 200 capacity, and you set uCount max to 200, you can fit many tasks on this CPU, and you won't get 200 bandwidth.
Can we take it offline then?
Yeah.
Because we are out of time.
Yeah.
Okay. Then it's
Okay.
awesome. Thank you.